Two coding models, same benchmark, same day. On the first test, they tie, 93.1 against 93.0. On the second test, one of them holds at 76. Other models on the same benchmark collapse to 27. Nothing about the models changed. The only thing that changed is the shape of the hole they were asked to fill. One of these models writes text the way you'd expect, left to right, one token at a time. The other one is a diffusion model, the thing that makes images. Diffusion took over image generation completely. So why is it now writing code, and why did the newest image models start doing the opposite? Here is the whole idea, and it is genuinely simple. Take an image, add a little noise, add a little more, keep going until there is nothing left but static. That direction is easy, anyone can add noise. The model never learns it. What the model learns is the other direction. Given something noisy, make it slightly less noisy. Do that enough times, starting from pure static, and an image falls out. The paper that made this work is from 2020. Ho, Jane, and Abil. De-noising diffusion probabilistic models. State-of-the-art on Chief R10 at the time, an FID of 3.17. One line in that paper matters more here than any of its pictures. Quoting the paper directly, we set t equals 1,000 for all experiments. 1,000 passes through the network to make one picture. Now hold that against how a language model writes. A language model produces one token, then the next, then the next. Each pass through the network commits one position, permanently. A diffusion model touches every position on every pass and commits nothing until the end. Those are not two philosophies. They are two settings of the same two dials. How much of the answer do you touch per pass? And how many passes do you take? Autoregression sits in one corner, one position, and as many passes as there are tokens. Diffusion sits in the opposite corner, every position, and a fixed number of passes that has nothing to do with the length. Everything in this video is a point somewhere between those two corners. Start with what the shape actually buys you. Because a diffusion model sees every position on every pass, it conditions on what comes after the gap as naturally as what comes before. Filling in a hole is not a special mode, it is just the normal mode with more of the answer already known. An autoregressive model has to be trained specially to do that. It reads left to right, that is the whole deal. That matters more for code than for prose. Nobody writes code left to right. You write a function, you go back, you change the middle. So here is that benchmark from the start of the video, in full. Mercury is a commercial diffusion language model. CodeStral is autoregressive. Both are asked to fill in missing code. When the whole is one line, they tie, 93.1 against 93.0. When the whole is a random span, several tokens, anywhere, Mercury gets 76.5. CodeStral gets 72. That gap is small. Keep watching the column. Quencoder scores 89.6 on single lines and 56 on spans. Claude Haiku scores 63.6 and 27.4. The autoregressive models do not degrade on spans, they fall off a cliff. That is the theory being confirmed, not a vibe. Filling a contiguous hole is exactly the case where touching every position should help. It is exactly where the gap opens. Now the harder question, if diffusion is so good, why do people keep saying it is over in images? Because three completely different things changed, and everyone calls all three of them diffusion. The first was the maths. Go back to those 1,000 steps. Why does it need so many? Because the path the model walks from noise to image is curved. To follow a curve numerically, you have to take small steps, or you fall off it. So the obvious question is, what if the path were straight? A straight path has constant velocity. One step lands exactly where 1,000 would. That is rectified flow. The paper's own claim is high-quality results with, and I am quoting, a single Euler discretization step. Before that, in the same year as the original diffusion paper, DDIM had already got sampling 10 to 50 times faster in wall clock terms. 1,000 steps, then a few dozen, then one. That is what actually happened to diffusion. It got shorter. On our two dials, that is a move straight down, same everything else, far fewer passes. Stable Diffusion 3 is built on it, so is Flux. When people say diffusion today, they mostly mean this. Though the paper is charmingly honest about it, rectified flow was, and I quote, not yet decisively established as standard practice. The second change was the backbone. The U-net that every early diffusion model used got replaced by a transformer. Image models now scale with exactly the tricks language models scale with. One of them, High Dream, is a sparse diffusion transformer. Mixture of experts, inside an image model, and the third change is the one that gets the headlines. In March 2025, OpenAI replaced DALL-E inside ChatGPT, and in the system card for what replaced it, there is one sentence about the architecture. Quoting it directly, unlike DALL-E, which operates as a diffusion model, 4o image generation is an autoregressive model. The company that made diffusion famous for pictures shipped its successor. The successor is autoregressive. That is one sentence, and it is all they published. Whether a diffusion decoder sits at the end of that stack is still argued about, and nothing OpenAI has released settles it. So take a model that documents itself. GLM image is a 9 billion parameter autoregressive generator, followed by a 7 billion parameter diffusion decoder. Not one or the other, both in sequence. Images did not abandon diffusion. Images started putting autoregression in front of it. While that was happening to images, the traffic started moving the other way. Mercury from Inception Labs is a commercial language model built on diffusion. Not a research demo, you can buy it. 1100 tokens a second on an H100. The smaller model, 737 for the larger one. The paper claims up to 10 times faster than speed-optimized frontier models at comparable quality. On Copilot Arena, it ranked second on quality and first on speed. Those are real numbers on real hardware. This is not a curiosity. And that paper is from 2025. This July, they shipped Mercury 2, a reasoning model, and by the company's own count, about 1,000 tokens a second on Blackwell. Then there is the author list, which I did not expect. Stefano Ermone is on it. He is also an author on DDIM, the paper that made diffusion sampling fast in 2020. Volodymyr Kuleshov is on it too. Hold that name. He comes back at the end of this video arguing against his own model. Diffusion can write code quickly and commercially. If it is this fast, why is everything you actually use still autoregressive? To answer that, we need the result that reframes the whole comparison. Think about what a masked diffusion language model is doing when it trains. It hides some tokens, predicts them, and unhides them. The order it unhides them in is random. So over the course of training, it is learning to predict tokens in every possible order. That sounds like a different thing to next token prediction. It is not. In 2024, a paper worked out that the objective these models train on is the same objective an any order autoregressive model trains on. Their words, the upper bound on the negative log likelihood for the diffusion model can be interpreted as an expected negative log likelihood for any order autoregressive models. In 2025, a second paper made it sharper. The title says it, Masked diffusion models are secretly learned order autoregressive models. It proves the objective decomposes into a weighted sum of autoregressive losses, one per ordering. So a diffusion language model is not a rejection of next token prediction. It is next token prediction that was never told which token is next. That claim is easy to overstate, so here is exactly what it says. It is a statement about the objective, the thing being optimized. It is not a statement that the two models are interchangeable. They train on the same thing, they decode completely differently, and the decoding is where all the speed comes from. It is also where all the problems come from. When an autoregressive model writes its 100th token, it does not recompute the first 99. It stored them. Every key and value it already worked out is sitting in memory, waiting. That is the KV cache, and it is the single largest reason language model inference is affordable at all. It works because of causality. Token 1 cannot depend on token 50, so token 1's answer can never change. A diffusion model has no such guarantee. Every position attends in both directions. Every position can still change, so nothing can be cached. Every step recomputes everything. The cruel part is the symmetry. The property that makes diffusion parallel is the same property that makes it uncacheable. You cannot have one without the other. Touching every position is why it is fast and why it cannot stop paying for it. Mercury's 1100 tokens a second are real. They are achieved while giving up the biggest optimization its competitors have. There is a lot of headroom in a number 1 that way. So the field did the sensible thing. It went looking for the middle. Here's the part that made this video worth making. 2 communities, starting in opposite corners, working on different problems, arrived at the same answer within months of each other. Start with text. If diffusion cannot cache because it has no causal structure, give it some. Not all of it, just enough. Instead of 1 token per pass, or every token per pass, you commit a set of tokens per pass and the sets are ordered. Inside a set, everything is parallel. Between sets, there is an order, and an order is all a cache needs. The first version of that idea is called block diffusion. Same group, 2025, and the subtitle on the paper is interpolating between autoregressive and diffusion language models. This July, they made the blocks flexible and called it set diffusion. Its architecture is described as set causal, and it supports KV cache updates after every inference step. The cache comes back. It was never diffusion that forbade it. It was the total absence of order. And the senior author is Vladimir Kuleshov, the same name from the Mercury paper. The person who shipped the fastest diffusion language model in the world is also the person publishing the argument for putting the order back in. That is not a contradiction. That is what it looks like when a field is actually working. Now the image side, which got there independently, GLM image, again, autoregressive generator, diffusion decoder. Order at the top, parallelism at the bottom. There is also a line of work with names like ACDIT, which describes itself as interpolating between autoregressive modeling and the diffusion transformer. It denoises 1 block of the picture at a time, conditioned on the blocks already finished. And its paper reports the same prize set diffusions does, decoding that can make full use of the KV cache. 2 fields, opposite starting points, and 3 papers with the same word in the title. But the word is not the finding. The finding is that both of them bought the cache back, and both of them paid for it the same way by putting an order on the thing. So, where are diffusion models in 2026? They are not obsolete, and they did not win. Both of those framings assume it was a contest between 2 different things. It was never 2 different things. It was 2 corners of 1 design space, and both corners turned out to be bad places to stand. Pure autoregression cannot use the hardware it runs on. 1 token per pass, on a chip built for thousands of parallel operations. Pure diffusion cannot stop recomputing. Every step, every position, forever. What shipped is the middle. Sets instead of tokens, straight paths instead of curved ones. Order where you need it, parallelism where you can afford it. The people making that argument are the same people who built diffusion in the first place. Ehrman, on the paper that made it fast and on the model that made it commercial. Rombach, on stable diffusion, and then on the paper that replaced its maths. Nobody defected. They just kept turning the dials. The next time someone tells you diffusion is dead, or that it is about to replace transformers, ask them which corner they think anything is standing in. Every paper in this video is linked below. The 2 with secretly in the title are the ones I'd start with. And the only reason this video exists is that somebody asked for it. Under the last one, Purple Lobster 42 left a comment. Would love to hear about diffusion next. So, here it is. That is the entire selection process. If this was worth your time, a subscribe genuinely helps. And tell me in the comments what to take apart next. Somebody down there is picking the next one.